All right, welcome to the Explainer. Today we're going to tackle a type of trigonometry problem that, let's be honest, looks way more intimidating than it really is. We are going to unmask these tricky equations and give you a simple, repeatable strategy to nail them every single time.
So a lot of us hit a wall when we see an equation with a trig function that's squared right next to a regular one. It feels like this totally new, complicated beast. But we're going to start by showing you that this problem is actually a familiar foe, just in disguise.
Okay, take a look at this. If your first reaction is a little bit of panic, you are definitely not alone. I mean, it doesn't look like a simple equation where you can just isolate theta. But what if I told you you've already solved problems exactly like this one? Just, wearing a different costume.
The key, the absolute secret to defeating this monster, is a super powerful but really simple technique called U substitution. It's what lets us transform the problem into something you already know how to do.
That's right, the whole secret here is just pattern recognition. This isn't some crazy high-level trig magic, it's just a standard quadratic equation, the kind you solve back in algebra, only it's wearing a clever cosine or sine mask. Our job is to just pull that mask right off.
Now, this is the slide where it all just clicks. Look at them side by side. The structure is totally identical. The only difference is that wherever you see a sine theta on the right, you see a plain old u on the left. Once you see that connection, the path forward becomes crystal clear.
And here it is. This is our game plan, a 5-step strategy that's going to work every single time. We substitute to reveal that hidden quadratic, we solve for our new variable u, and then this is important, we substitute back to find all the final angles. So let's put it to work.
All right, let's get our hands dirty. We're going to walk through 3 different examples straight from our source material. You'll see how this one strategy can handle everything from the simple cases to problems that need a little more algebraic muscle.
First up, the most straightforward type. This is the friendly version. The hidden quadratic here is one that we can solve with some simple factoring, just like you did in algebra class. No scary formulas needed for this one.
So step 1, we just say, let's let u equal sine theta. Instantly, that messy equation transforms into 2u squared minus u minus 1 equals 0. And what do you know? That factors beautifully into 2u plus 1 times u minus 1 equals 0. So much cleaner, right? Now, from that factored form, it's easy to see our 2 solutions for u. We get u equals 1 and u equals negative 1/2. Now, there's a really crucial check we have to do here, which we'll talk more about later, but for now, just know that both of these values are valid for sine, so we get to keep both of them.
And now for the final step. We just substitute back. We have to solve sine theta is equal to 1, which gives us pi over 2. Then we solve sine theta is equal to negative 1/2, which gives us 2 different angles on the unit circle, 7 pi over 6 and 11 pi over 6. And there they are, our 3 final solutions. Beautiful.
Okay, but what happens when it doesn't factor so nicely? Well, for our next example, we don't panic. We just call in our old trusty friend, the quadratic formula.
So after we substitute u for cos theta and plug it all into the quadratic formula, we get our first root. U is about negative 0.382. So we ask the question, is this a valid value for cosine? Yes, absolutely. It's between negative 1 and 1, so this one's a keeper.
But now look at the second root the formula spits out, about negative 2.618. Now think about it. Can the cosine of an angle ever be negative 2.618? No way. The cosine function is always trapped between negative 1 and 1. So we have to reject this root. It's a valid mathematical answer to the quadratic, but it's not a possible answer in trigonometry.
So we only move forward with our one valid root. We just grab a calculator and find the angles where cos theta is about negative 0.382. This gives us our 2 final solutions, approximately 1.955 and 4.328 radians. All right, now for a really fascinating case. What happens when the hidden quadratic itself doesn't even have any real solutions? This problem looks pretty innocent, but it's hiding a totally different kind of secret. When we use the quadratic formula here, we end up with a negative number under the square root. Now, what does that mean? It means our solutions for u are complex numbers. And since the sine of a real angle can never be a complex number, it means this equation has no real solution at all. Case closed. This brings us to what I think is easily the most critical part of this entire process. Seriously, this is the step where most mistakes are made. It's the one check that separates a right answer from a wrong one. You have to burn this rule into your brain. It's non-negotiable. After you solve for u, you must check if it falls in the valid range for sine or cosine, which is always from -1 to 1. If it's outside that little window, like 1.5 or -3, you throw it out. Simple as that.
And this is exactly where people get tripped up. They'll just blindly plug arcsine of 1.5 into their calculator, get an error, and not know why. It's because the value was impossible to begin with. Or they'll forget to check both roots from the quadratic formula. Think of this range check as your most important quality control step.
So you might be thinking, okay, this is a neat math trick, but when am I ever actually going to use this? Well, it turns out this exact skill, solving an equation and then checking if the solution is physically possible, is absolutely critical in a ton of science and engineering fields.
Just take optical engineering, for example. When they model how light bends as it passes through different materials, the equations they use can look just like the ones we've been solving. They find the angles, but then they have to discard the solutions that don't make sense in the real world, what they call the non-physical roots. It is the exact same logic we just used.
So we've seen today how a problem that looks like a monster can be unmasked to reveal something familiar, something totally manageable. And that leads to a bigger question, right? What other complex-looking problems, not just in math, but in any subject you're studying, are actually just a simple idea wearing a clever disguise? Something to think about. Thanks for joining me.